In our last lesson, we reviewed that a confidence interval is a range of values for a population parameter, and we also use GeoGebra to find confidence intervals for single samples. In this lesson, we're going to extend that idea to compare two populations, which means that now we're going to be working with two samples. We're going to be using confidence interval formulas and GeoGebra commands, depending on whether we're comparing means or proportions, and whether we know the population standard deviation or not. Before we jump into the examples, I want to walk you through these two reference charts on the first page. The first one shows the different confidence intervals for two samples. And then the second table is our interpretation table, which is going to help when we get to the interpretation table. That's going to help understand why we have the difference between our sample statistics as our point estimate. Okay, so let's look at the first table in the first row. This first row is for a confidence interval, a t-interval for the difference of means, which is why we have x1 bar minus x2 bar as our point estimate. We're talking about the difference, meaning subtraction of means. Okay, so x bar 1 goes with the first sample, and x bar 2 comes from the second sample. And you can see that we have our error formula here. And because we do not know what the population standard deviations are for each of those populations, notice that instead of using sigmas, we're using the sample standard deviation. Now this N1 is the sample size from the first sample, and N2 is the sample size from the second sample. And then of course we have our T critical. So we would still use these formulas to calculate the error, and then we would add and subtract from the point estimate so that we can get our confidence interval. Now, we also need to know when we're doing a t-interval for the difference of means that the samples are independent and random. So those are also necessities. Let's look at the second row. This is another confidence intervals for the difference of means, but this time we do know what sigma 1 and sigma 2 are, our population standard deviations for both of the populations. And because of that, in this formula, we would use the population standard deviation rather than the sample standard deviation. This doesn't happen too much in real life, but if we do run into it, we'll know how to handle it. Okay, so we also need those samples to be independent and random, and the point estimate is going to be the same as for the t-interval. It's the difference between the two means. Now, the third row is for a z-interval difference of proportions. So we're going to have a different formula, but because we're going to be estimating the binomial distribution with the normal distribution, we're still going to be using z-critical for our critical value. Our formula is going to have p's and q's in it instead of sigmas because we're dealing with proportions. And p1 and q1, those are the values for the probability of success and the probability of failure from the first sample. And then p2 and q2 are the probability of success and failure from the second sample. And then you can see here, because we're dealing with proportions, the point estimate is the difference between the probabilities of success between those two samples. Now, in order to use these intervals, just as all the other ones, the samples need to be independent and random. But to make sure the sample size is big enough, we need to take n times p and n times q for each sample and make sure that in all cases it's greater than or equal to 5 to make sure that our sample size is big enough. All right, let's take a look at the interpretation table now. Something that I want you to think about is if I take two numbers and I subtract them, let's say I take 20 minus 10, that gives me a 10. That gives me a positive value because 20 is the bigger value. But if I reverse that, if I did 10 minus 20 and I got negative 10, this is negative because 10 is smaller. So the bigger number here still is 20, but because I'm subtracting 20 from a smaller number, that's why it's negative. Now, if I apply that idea to our population parameters, let's say I take mu1 minus mu2, and I say that mu1 minus mu2 is between 10 and 20. That tells me, because mu1 minus mu2 is between two positive numbers, that mu1 minus mu2 itself, if I knew what those values were and I subtracted them, they have to be positive. So mu1 minus mu2 has to be positive. And if mu1 minus mu2 is greater than 0, that tells me that mu1 has to be bigger than mu2. So when we set up our point estimates, we do that so that we can see what kind of interval it lies on. Does it lie between two positive numbers? Then that tells me that mu1 has to be the bigger of the two values. Now it works in the other direction as well. If I said mu1 minus mu2 falls between two negative numbers, like negative 5 and negative 1, then mu1 minus mu2 has to be a negative number, which tells me that mu2 has to be bigger. Because if mu1 minus mu2 is negative, then you're taking a smaller number minus the larger number to get a negative number. So in this case, we would say mu2 is greater than mu1. Then lastly, if I gave you mu1 minus mu2 is between negative 5 and positive 5, we have no idea if that difference is negative or positive, because that difference could be, say, negative 2, or it could be positive 3. Both of those values fall between negative 5 and 5. So when it's between a negative number and a positive number, there's no way to know which one is bigger in this case. We would have to do more research. So this information that I just went over with you is what's in this chart. It's summed up here. So if you take your two population parameters and it falls on an interval where your upper and your lower bound are both positive, then that has to mean that mu1 is greater than mu2, or P1 is greater than P2, depending on if you're talking about means or proportions. If your point estimate lies on an interval and your upper and lower bound are both negative, then that tells me that mu1 has to be smaller than mu2, and P1 has to be smaller than P2, depending on if you're looking at means or proportions. And then if your upper and lower bound are different signs, there just isn't enough information to draw any conclusion. Let's look at example 1. A marine biologist is studying the average size in centimeters of lobsters found in two different bays in Maine. We have Casco Bay and Penobscot Bay. The following random samples of lobster lengths were collected. So these represent the lengths of the lobsters in each data set in centimeters. We need to construct a 95% confidence interval to estimate the difference in the true mean lengths of the lobsters between Casco Bay and Penobscot Bay. So we're looking at the difference in the means. So that means that we're going to be using a t-interval or a z-interval for differences when we're dealing with the means. So we are not provided the population standard deviation in this case for either population. So we're going to have to use a t-interval for the difference in means. All right, so make sure your spreadsheet is pulled up because we're going to need that. Pause the video and enter these values in. I put Casco Bay values in column A and Penobscot Bay data in column B. I already have mine in there preloaded, but take a minute, pause the video, and enter your data. Okay, now that you have your data in, you want to make sure that you select, you're doing a t-estimate for your t-interval for the difference of means. So this is what we're doing now with two different samples. I'm going to make sure I'm on that. Now, for each sample, I need to know the mean, the sample standard deviation, and the sample size. So I'm going to highlight the data from sample 1. I'm going to choose the histogram icon and choose one variable analysis. Let me make a little bit of room here. Then I'm going to click on the button to show statistics. And we've got that the sample size is 10 for the first sample size. We've got a mean of 25.58. I'm going to put that in here. I got a sample standard deviation. My S is 0.5653. And we already have our sample size in there. So now we have to find all that same information for the second sample. So then I'm going to highlight my data from column B. I'm going to choose Show Statistics. I'm going to click on One Variable Analysis and Show Statistics. And then we can see here that the sample size is 10. We have a mean of 24.51. And our sample standard deviation is 0.3957. Okay, so we have all of our information in there. We want to make sure that this pooled option stays unchecked. When we scroll down here, we can see that, where are we at? Our lower limit is 0.6077 and our upper limit is 1.5323. Here is our point estimate, 1.07, because I take the difference between the two means. And then here's our error. We add and subtract our error, 0.4623. So if you want to try that error formula to see if you get the right answer and practice with the formula, you can certainly check it here. All right, so let's write down our answer. Our confidence interval is 0.6077 to 1.5323. That tells me that I'll use M for mu, but this is really should be a mu. Our mu1 minus our mu2 is between 1.5323 and 0.6077. Now, because the difference of these two means fall between two positive numbers, then when I subtract these, I should actually get a positive number because a positive number has to fall between two positive numbers. What does that tell me? If I take mu1 minus mu2 and that gives me a positive value, that tells me that mu1 must be the bigger number. So what we're getting from this is that mu1 is greater than mu2. That's what we're getting out of this. So our conclusion would be we are 95% confident that the population mean of the lobster lengths in Casco Bay are longer than the lobster lengths in Penobscot Bay.